Okay, welcome to this video. This is a part of a sequencing series, and it's on sigma notation and recurrence relations. Those are the two sections which we're going to cover. So sigma notation refers to this way of writing the sum of some terms in a sequence, i.e. a series. Now, firstly, I'm going to run through exactly what this means. So it's called sigma notation because the Greek letter sigma is this this letter here, and that's a capital sigma. A lowercase sigma would look like this, but we use that in statistics sometime for standard deviation. But this capital sigma means sum. S sigma for sum, the Greek letter equivalent of S. And so what this means that I've got written here is sum. That's the part that looks like this. From k equals 1, and that's the red part there, to k equals 3, and that goes up to the top there. The expression 2k, and that's what this interpreter means. And we could change where we sum from. We could sum from a different number up to a different number, and we could change what we sum each time. Now what you do is you in turn substitute values of k from 1 up to 3 into the expression and then add them all up. So we could start with k equals 1. If I put k equals 1 into that term, then I get 2 times 1. And now I add to that what happens when I put k equals 2 into that expression. So that's 2 times 2. And I add to that what happens when k equals 3 into that expression. And so I get 2 times 3. Ooh. Like that. And so we can see what we get overall is 2 plus 4 plus 6, which is equal to 12. And so the sum from 1 to 3 of 2k is equal to 12, and we've worked it out. Okay, let's do another example of this one. So this is sum from 1 to 3 of 2k plus 1. So if I put k equals 1 into that expression, I get 2 times 1 plus 1. That's that expression. Now I want to put k equals 2 into that expression. So I add to that 2 in brackets 2 plus 1. Note that the 1 just doesn't get anything. When we substitute k into 2k plus 1, it just is still 1. And we add to that when k is equal to 3, and that is 2 times 3 plus 1. And then we just need to work this all up. So we've gone from k equals 1 to 3. So that is 2 plus 1 plus 4 plus 1 plus 6 plus 1. We've got the 12 that we had originally, 3 more 1s, and so we can see that this adds up to 15. Okay, let's do another example, with a bit more going on. So if I put k, well, I've got to start at k equals 3 here, so I start with k equals 3. I put it into this expression very carefully, and I can see I've got 3 times 2 to the 3 minus 1. If I put k is equal to 4 into it, because I'm going from 3 to 5, I add to that 3 times 2 to the 4 minus 1. And I add to that 3 times 2 to the power of 5 minus 1, because that is what happens when I get k is equal to 5. Simplify that. 3 times 2 squared plus 3 times 2 to the 3 plus 3 times 2 to the 4. Now I could literally calculate what this is. I might want to factorize out 3 times 2 to the 2 squared. I can factorize that out there and get 2 plus 2 squared. So whatever way I want to do it, I could just work out what I get. Oh, I just made a little mistake. I can see that I should have a 1 plus here. So it's 1 factorizes from there, 2 from here, 2 squared from there. And so I get 3 times 4 times, that's 7. So that's 12 times 7. So that is 84. Okay, so before I carry on, you might actually notice that these look slightly familiar, some of these things that I've had in here. Well, these feel a bit like arithmetic or geometric sequences. If I go back to this one here, well, this each time, if I look at each term, I'm going to remove that 15, I get 3 plus 5 plus 7. This is an arithmetic sequence with a equals 3 and d is equal to 2 and n is equal to, well, it's the first 3 terms of that. Well, we could have worked out what the sum of the first few terms is using a formula. So you can see this really is just kind of a similar thing. We would end up with the same thing. You're kind of rewriting it. Another thing to note is that the nth term of that sequence, which would be a plus n minus 1 times d, which in this case would be 3 plus n minus 1 times 2, which would give me 2n plus 1, and that there is the same as what we see in here. So this is the nth term if we wanted to use this summation notation for summing something, a sequence which we had the nth term of. If we go into this one here, if I add in what each term was equal to in this line here, we can see that this is 3 times 4 is 12, and this is 24, and this is 48. And we can see that what's happened here is we have got multiplying by 2 going on. And indeed, this does look like the nth term of a geometric sequence, which is ar to the n minus 1. And in fact, if we had started here at 1, then we would have got a as being the first term in the kind of the right way that we would be expecting. So again, this is the nth term of a geometric sequence, which leads us to summing up to n terms. So I could start to input this into here. So I could put k equals 1, and I'd get 3 times 1 minus 1. And then I could get k equals 2, and I could put 3 times 2. But then I get to a problem because I don't know when to stop. I would have to keep going forever. So I don't know how big n is. So I'd stop at n, but I don't know how big n is. So what have I got going on here? I've got 3 minus 1. I've got 2. I've got 5. The next term, well, let's do one more. K is equal to 3. I'd get 3 times 3 minus 1. Which is 9 minus 1. So that's 8. And I can see that this is an arithmetic sequence with a equals to 2 and d equals to 3. And we know that the sum of the first n terms has a specific formula. Well, they're the same. This is the sum of the first n terms. This is Sn for that arithmetic sequence. So Sn is equal to the sum of the first n terms, so it's from k is equal to from 1 to n of 3k minus 1, but we've got a formula for that, and the formula that we have is n over 2 2a plus n minus 1 times d. Well, we don't know n, so it's still n over 2, but we do know that this is 2 times 2 because we know a is 2, plus n minus 1 times 3, because that is what our value of d is. Let's give myself a bit more space. Okay. So this is equal to n over 2, open brackets, 4 plus 3n minus 1. So this is equal to n over 2, in brackets, 3n no, minus 3 here. So 3n plus 1. So that is a way of expressing this. I can see that overall, this is equal to n over 2, 3n plus 1. So we have managed to sum it. Okay, what I'm actually going to do now is to show you how you can use the calculator to do all of these things. You will need to do these by hand if you don't know the exact values of stuff, but the calculator can do these things for you. And that's using this button here, which I am moving my mouse around here. Now you need to press Shift and then the X button, and it brings it up with that exact notation that we had before. So we got 84 when we calculated this value here. I'm going to go back to going from 3 here. So let's have a look what we get. So if I start at 3, let's just make sure I erase that properly. Okay, right, so I want to sum 3 times 2 to the k minus 1. Now, I can notice that in here they've put x here instead of k. Doesn't matter, it doesn't matter what letter that is at all. 3 times 2 to the power of, and I need to put x using this button, minus 1 up in the power. Then I click right, and it goes down to the bottom here. I want to go from 3 up to 5. And if I click equal, it sums it for me, and I do it for 84. So the calculator can do it very quickly. I'll do another one. I check that this value here, we should get a value of, well, let's see what we get. So I do that, Shift here, 2x plus 1 from 1 to 3. And it gives me 15, which is the value I got before, if I remember. Okay, so let's go back down to where we're up to. And what I want to show you here is 2 important sums that I reckon you should remember and have an awareness of them coming up. And that is that we're going to sum from, and I've just changed the letter here to R, but it could be K, it could be X, it doesn't matter, from 1 up to N of 1. So sometimes you can get a bit thrown off by this one, but if R equals 1, what does 1 equal? Well, it equals 1. If R equals 2, what does 1 equal? It still just equals 1. R equals 3, 1 equals still 1. And what you do is you're going to add up 1, but we're going to add up 1 n times. And if you add up 1 n times, you can see that this is just equal to n. So to put it out there, this is equal to n. And what about this next one? Well, I'm going to leave a gap here for putting my answer. If I put r equals 1 into r, when r equals 1, I get 1. When r equals 2, I get 2. When r equals 3, I get 3. And so on up to r equals n, I get n. So this is the sum of the first n integers. We saw that in video 1. This is the Gauss's trick. So we know that if n was 100, we could do that thing where we write it backwards and forwards. Well, we've also got formulas for this now. And what we're going to see is that, well, if a equals 1 and d is equal to 1, because that is an arithmetic sequence where we start at 1 and we go that, and we've got n terms, we know that Sn is equal to the formula. So we've got n over 2 times a plus n minus 1 times a, 2 plus n minus 1, n over 2, n plus 1. And overall, the formula is n plus 1 over 2. Now, you can always work this back out just from using the formula that you know, but it can be very handy to just remember this like this. Okay, I'm actually going to say to you at this point that you could try some of the questions on summation notation right now. However, I'm going to carry on in this video and do recurrence relations as well, because, well, I think we could do those things. So I might have said recurrence relation before. You could do some questions on sigma notation right now. That is exercise 3F. But I'm going to carry on to do recurrence relations, and you could do all of the questions all at once. I'm also going to go through an exam question that covers both. So I'm going to go on to recurrence relations. This is a recurrence relation, and it comes in two parts. Now, it is not something to be too intimidated by. I think the thing that there's a lot going on the page, but what you need to do is to just think about it in this sense. So this is the start, and this is the rule. Now the start just says that A1 is 3. It just says that the first term is 3. So we can write that down. That's okay. The rule says, and then need to interpret this, that if you had the nth term, which was an, and you add 4, then we get an plus 1, which is the next term. So if you imagine putting n as 1 in here, this would say that a1 plus 1, so a2, is equal to a1 plus 4. So just look at that again. If I put n as 1 in here, an is a1, and an plus 1 is a2. Well, we know a1 is 3, so I can substitute that in there to say 3 plus 4, and that gives me 7. So I know that a2 is 7. Another way of putting this in words is add 4 to the previous to get the next. And that is a good way of looking at what that exactly says. So now if I try a3, that's going to be a2 plus 4. So that's what happens if I put n equals 2 into the rule. And so I get a3 is a2 plus 4. Well, that is 7 plus 4, which is 11. And we could carry on onwards and onwards. Now, what you might have noticed is the sequence that we've got is 3, 7, 11, and the next one would be 15, and we've got an arithmetic sequence. Well, this isn't that surprising, because what we've said is that the rule is you add 4 to the previous term to get to the next. Well, that is an arithmetic sequence. So from this, you could find the nth term by using the formulas. You could find the 50th term because we know it's an arithmetic sequence. Okay, here's another one. If we had a is equal to 4 and an plus 1 is equal to kan plus 2. Well, I added this in because I thought the k, it's useful for us to kind of be aware that there might be unknowns in here. We might not always know everything about it. So a1 is equal to 4, we know that. a2 is equal to k times a1 plus 2, which is equal to k times, well, we know that a1 is 4, 4 plus 2, so this is equal to 6k. Now, I don't know what k is. a3, that's going to be equal to k times a2 plus 2, which is equal to k times 6k plus 2, so that's equal to 6k squared plus 2k. So this could be the start of a question where they then tell you the sum of the first then 3 terms, and they say that the sum of the first 3 terms equals 27, find k. So that could be the kind of question that we get here. But all I'm doing is I'm using this relationship. If I was to try and put this into words, I'm maybe not going to write it down. It says take the previous term, add 2, multiply by k, and that gives the next term. And that's what that rule would be described as. Okay. Here's quite a famous one. I'm going to pause and I'm going to say, can you tell what this is? The hint is this is a famous one. Pause the video if you want a bit longer. Okay, Well, this has given us A1 and A2. And the reason for that is that to work out, we can't get the next term from the previous. We need the previous two terms. And that might be an even more hint if you hadn't worked it out. So I'm going to start writing them down. A1 is 1. A2 is also 1. A3 is going to be equal to A1 plus A2, which is 1 plus 1, which is 2. A4 is equal to A2 plus A3, the previous two terms. 1 plus 2 is 3. A5 is going to be the previous two terms. That's going to be 2 plus 3. That's going to be 5. And the sequence that we've ended up with is 1, 1, 2, 3, 5, 8, 13. And if you don't recognize it already, it's the Fibonacci sequence. So the Fibonacci sequence is one that can be written quite easily with a recurrence relation. Okay, I'm going to do an exam question now, which kind of uses both these two things, the recurrence relations and the summation notation, and hopefully this can be useful. Okay, so I'm having a look at the exam question. Give myself a bit more space here before I start part B. So we've got A1 is 1, and it says find A2 and A3. So we're going to do exactly that. So A1 is 1. A2 is equal to K times, in brackets, A1 plus 1 divided by A1, which is equal to K times 1 plus 1 over 1. So it's 2K. A3 is K times A2 plus 1 over A2. So it's K times 2K plus 1 over K, over 2K, sorry. Bit of simplifying, this is 2K plus 1 over 2. Right, let's look at the next part of this question. So we've brought in the summation notation now. And it says, given that the sum of the first three terms from 1 to 3 of this sequence is 10, find the value for K. Right, so the sum from R equals 1 to 3 of AR, well, that's just going to be A1 plus A2 plus A3. I'm putting R as 1, R as 2, and R as 3 in. That is the sum of the three terms. Well, we have these up here. So it is 1 plus 2K plus 2K plus 1 over 2. And we know that this is equal to 10. Find K. Well, we don't have any recurrence relations. We don't have any sigma notation now. We've just got an equation. I would be tempted to immediately get rid of any fractions. So this is 2 plus 4K plus 2K plus 1 equals 20, multiplying everything by 2. And I can see the left-hand side is going to be 6K plus 3, and that is equal to 20. And so that is 6K is equal to 17. And so overall, K is equal to 17 over 6. Not a very nice number particularly, but it is nevertheless the value of K that would mean that the sum of those first three terms was that. Now note that we don't know the nth term of this sequence. I could check my answer, but it's not arithmetic, it's not geometric. So it's just a different kind of sequence. Not all sequences have to be arithmetic or geometric. But nevertheless, that question is done. Okay, now I recommend that you have a go at these questions. I put up the exercise 3F ones before. If you might have already done those at this point, have a go at 3G. Broadly speaking, this is the sigma notation stuff, and this is the recurrence relation stuff. So have a go at those questions now. In the next video, I'm going to do some kind of exam questions and also modeling these exam questions, which is the last part of sequencing series.